Okay, let's go ahead and continue with molecular orbitals. Okay, in this case, we're going to be doing helium. So each helium atom has its 1s2. This is 1s2. Again, when we make our sigma bond, this is a 1s sigma. This is a 1s sigma star. Now in this case though, remember we're looking at 1, 2, 3, 4 electrons from our 2 helium atoms. So when we fill in the electrons in our molecular orbitals, 1, 2, 3, 4, you'll find that we filled in both our sigma and our sigma star. So if we determine bond order, okay, 1/2 of 2 electrons minus 1/2 of 2. Remember, it's 1/2 of all my bonding electrons minus 1/2 of all my anti-bonding electrons. So my bond order is equal to 0. So we never observe a helium-2 because what we see here is there's no bond that's able to form between the two. Now if you say, oh, well that's kind of obvious, I know it is, and that's the nice part. Don't think that this is a bad thing. What's nice is we're seeing consistency across all of our different methods. If we find that there's no consistency, then there's most likely an issue that we have to resolve. But in this case, we know helium is a noble gas, doesn't form helium-2, bond order is 0. Hydrogen forms hydrogen gas, it's H2, bond order is 1. Now let's take a look at row 2. So we'll just do lithium for this one, and then we'll look at a few other ones because we have to look at the p orbitals. So for row 2 we have lithium-2. This is, remember, my homonuclear means the same nuclei, diatomic molecule, okay, that we're investigating. Now when we do that, what we're going to find is this. Lithium is 1s2, 2s1. So we're going to have 2 sets of molecular orbitals that we need to look at. Okay, so we have 1s, 1s, okay, and then we have 2s, 2s. And because they're the exactly same atom, my levels are exactly the same. So this is going to be lithium, and this is lithium. So let's take a look at what happens when we make our molecular orbitals. When you combine them, you're going to form, when you combine them, you're going to form this, right? And form your sigma, 1s, 1s. And you're going to get sigma star, the antibond, 1s, 1s. Now we're going to do the same thing with 2s. You're going to form sigma, 2s, 2s. And you're going to get sigma star, 2s, 2s. Okay, and I'll just draw my dashed lines so you can see how symmetrical it is. So how much it drops is the same amount as it goes above my non-bonding. These are my non-bonding energies. Okay, so now that we've made our orbitals, we now have to look at our electrons. And if we look at our electrons, we know it's 1s2, 2s1. lithium here. 1s2, 2s1. So I have 6 electrons to play with when I fill in my molecular orbital. And when I do that, then we find 1, 2, 3, 4, 5, 6. Okay? So, not surprisingly, these are my core electrons. So we remember valence electrons are what's really responsible for reactions and bonding. And we see that with the core electrons, all my antibonds, bonding situations, cancel out all my bonding situations. Okay? But right here, this is the key. So if we look at bond order, and I'm still going to go ahead and use all of them right now. And what we're going to do after this, bond order, not body order, bond order, 1/2, 1, 2, 3, 4, because I have 4 electrons in my bonding situations, minus 1/2 of 2 is equal to 1. So it's possible then to form a diatomic lithium molecule. Now before we say, oh wait a second, that's a metal, how can it be? I thought it was an atomic metal. So now suddenly we're saying that you can form a molecule. So when do we observe this? Not when we're playing with the lithium metal, but when we vaporize lithium, we actually can detect lithium-2. And so it is definitely possible to form a lithium-2 molecule. Okay, so it is detectable, and we see that we actually vaporize lithium. Okay, now let's go on. And what I'm going to do is from now on, I'm going to just focus on the molecular orbitals. Okay. Of my valence electrons. All right, so let me show you what I'm talking about. Let's talk about beryllium-2. How can we make it? It's a good question. So beryllium is 1s2, 2s2. Okay? And so when we do the same thing, and we're only going to be focusing on my valence electrons, 2s and 2s, then we're going to see you're going to get your sigma, 2s, 2s. You're going to get your sigma star, 2s, 2s. Okay? And when you do that, let's take a look at the number of electrons we have. Okay? We have 2s2. So my bond order is equal to 0. So we do not form a diatomic beryllium molecule. Okay? All right. So much for that. Let's take a look at those elements that have p orbitals. Okay? Now what happens is with the s, since we're talking about 1s and 2s, they don't interact. But now if we're talking about 2s and 2p, we have basically two situations. S and p have weak interactions, or my s and p orbitals have strong interactions. Okay, so what's the difference? Well, when S and P have weak interactions, when we draw our molecular orbitals, then basically my sigma 2p 2p is lower in energy. And it's going to be pretty much the same as what we've been doing. However, when I have strong interactions, what's going to happen is my sigma 2s becomes more stable, by the same amount of energy that my sigma 2p 2p decreases in stability. Now this doesn't seem so bad, but what happens when I have strong interactions, what you'll find is when we put our orbitals together, my pi 2p 2p orbitals are more stable than the sigma 2p 2p. Alright, so now that you have it written down, let's go ahead and show you the diagrams. I'm going to try to fit them side by side. Okay, now before we draw the diagrams, just be aware what elements have weak interactions and what elements have strong interactions. So boron, carbon, and nitrogen, these all have strong interactions. Okay? If you go to oxygen, fluorine, and neon, these all have weak interactions. Alright? So what we're going to do is let me draw my orbital diagram first. So you see what's strong and weak, and then we'll actually focus on two different diatomic molecules. Okay. So let's do our orbitals, and what I'll do is I'll put our strong interactions on the left hand side, and I will put our weak interactions on the right hand side. Okay, so let me go ahead. You know, this is my energy is increasing, and we're going to focus on 2s and 2p. Okay, so let's do, believe it or not, let's do my weak interactions first. So I have 2s and 2p, and I'm trying to give myself lots of space here. Okay, for the strong, likewise, we're starting off with 2s and 2p. Okay, so when we do our weak interactions, we're going to get basically our sigma 2s and our sigma star 2s. Okay? Now what about the 2p's? Well, remember something that I mentioned earlier, and we're going to apply it here, And that is the first bond that gets formed is always going to be a sigma bond. So what's going to happen is the first bond I form is a sigma 2p 2p. And any subsequent bonds are going to be pi bonds. Okay? Pi 2p 2p. Alright? And then equal and opposite energies. Pi star 2p 2p. And up here, sigma star 2p 2p. And the only reason I'm not writing 2p 2p for these guys is beginning to get really messy. Okay? It'll be hard to read. So I just want to kind of keep it that way. But you know these are going to be 2p 2p and 2p. So, what happens under strong interaction? So let's go through. We said, let's get my symmetry here. We said that this will improve on stability by the same amount of energy that this decreases. Okay, so what we were making was our molecular orbital diagram for those atoms that have weak sp interactions. So I have my sigma, this difference in energy between my s and my sigma should be equal to the difference in energy between my s and my sigma star. Remember, the very first bond that you make is always going to be a sigma bond. So you have a sigma 2p 2p, then your 2 pi 2p 2p's. Here I have my 2 pi star 2p 2p and my sigma star 2p 2p. And I try to fit it in, but you see it's getting a little messy. These should all be in alignment, so I apologize about my skew. But the bottom line here is when I draw these green lines is just to help indicate the symmetry of your molecular orbital. And for the weak interactions then, this applies to oxygen, fluorine, and neon. Okay. And as we mentioned earlier, when you look at strong interactions between my 2s and 2p, which would be like for boron, carbon, and nitrogen, this sigma 2s becomes more stable. So if I draw this and try to make it as uniform as possible, you can see that I've dropped this stability by about that much. What happens is that energy is compensated, because remember we have to conserve everything, by an increase of my sigma 2p 2p. So if I take my pi's here, what I've done is I've had to increase my sigma. Okay, so if it drops that much, then my sigma increase that much. Everything else stays exactly the same. Okay. Here's my sigma 2s 2s. Here's my sigma star 2s 2s. Okay. Now what's lower in energy are my pi 2p 2p. And then is my sigma 2p 2p. Alright? My pi stars here, 2p 2p, stay the same. And my sigma star, 2p 2p, stays exactly the same. So, let me go ahead and draw my dashed lines. And you can see this is no longer, well, symmetrical. This has become more stable. Likewise, the amount it's dropped is the amount that my sigma 2p 2p has increased in energy. So now, depending upon what diatomic molecule you'll be examining, you can determine which molecular orbital diagram you're going to use. If I say, oh, we have weak sp interactions, this is what the orbital diagram is going to look like. If I have strong sp interactions, then this is what the orbital diagram is going to look like. And what we're going to do is we're going to look at boron, B2, and we're going to look at oxygen, O2. Okay, so let's just take a look at two examples here. So we have an example of boron, the diatomic boron. And remember, boron, carbon, and nitrogen have strong interactions between their 2s and 2p orbitals. Whereas oxygen, fluorine, and neon have weak interactions. Okay, so let's do the strong interactions first. And also recall, the strong interactions, my sigma 2s becomes more stable, and the amount it becomes more stable is what increases the energetics for my sigma 2p. Okay, so normally we would just draw our diagram like here, 2s, sigma 2s, 2p, sigma 2p, then my pi stars, and my sigma star. Here, because of the small changes, this is due to strong interactions between my s and p orbitals. So now that I have my orbital diagram made, what I did was I'm looking at my valence electrons only, and I put in my electrons for boron. 2s2, 2p1. So 2 in the s, 1 in the p. And since it's diboron, we have 2 of each, right? I have a total of 4 electrons here, so 1, 2, 3, 4. I have 2 electrons total, so 1 here, 1 here. What that means is that boron acts as a diradical. I actually have 2 unpaired electrons in here, hence di. And an unpaired electron is a radical. When you have unpaired electrons, it gives paramagnetic properties, like the boron has magnetic properties, and the bond order for boron is going to be 1/2 of 1, 2, 3, 4 minus 2. So boron, B2, is going to be fairly reactive because I have the diradical, okay? And then, as well, you have to be aware that it's paramagnetic. And if you just thought about drawing the structure of boron, drew like BH3 for boring, we're not thinking about some of these properties in terms of its reactivity. And what's even more significant, or just as interesting, is if we did oxygen, which has a weak interaction. So my sigma 2s, the difference in energy here is equal to the difference in energy here. Here you can see this is larger. Okay, differences in energy here. And we know that oxygen is 1s2, 2s2, 2p4. And again, since I'm only looking at my valence electrons, 2s2, 2p4, which means I have 4 electrons total for my 2s, 1, 2, 3, 4. And I have 8 electrons total for my 2p. So 1, 2, 3, 4, 5, 6, 7, 8. So also, for oxygen then, it acts as a diradical. So it has paramagnetic properties. And we actually see that when we actually do studies with oxygen gas, that it actually has magnetic properties. Now if we draw the structure, so let's take a look at bond order. Okay, so I'm going to go ahead, I talked about bond order for boron, so I'm going to go ahead and erase this. And if we look at oxygen, the bond order for oxygen is going to be equal to 1/2 times 1, 2, 3, 4, 5, 6, 7, 8 minus 1/2 times 1, 2, 3, 4. That means 2. Well, that makes a lot of sense, because when we draw the Lewis structure of oxygen, don't we draw it like this? So, all we're saying is that doing molecular orbitals, we agree. Bond order is 2. It looks like just a pure double bond. There's no partial bond character to it. But when you draw this Lewis dot structure, the one thing we don't see and don't observe is from here, you wouldn't realize it acts as a diradical. Okay, so let's take a look at what we call a heterodiatomic molecule. And when we say heterodiatomic molecule, what we're saying is that two different atoms, okay? So, two different elements, okay? So we're talking about heterodiatomic. And the other thing I'm going to mention here, not always the case, is we'll only be doing examples where the interaction between S and P is weak. Okay? So that indicates to you what your molecular orbital diagram is going to look like. This is important information. The other thing you need to do when it's heterodiatomic is the lower energy S and P orbitals belong to the more electronegative atom. All right, so that's also important. So let's take a look at something like NO. All right, NO. You don't say, no, I don't want to look at it. We're going to anyway. All right, so NO, N is 1s2, 2s2, 2p3, O, 1s2, 2s2, 2p4. Okay, we are going to look at our valence electrons. Okay, and since we said it was a weak, here's my nitrogen, here's my oxygen. So if I look at my 2s, and I look at my 2p, all right, if I look for oxygen, let me give myself space. Oxygen's a lower energy, 2s, 2p. Okay? And I'm hoping I get enough, give myself enough space. And so just sleep. Okay? So, when we make our orbitals, then what we find is that my sigma 2s a little closer to my oxygen 2s. This is more electronegative, so it's lower in energy. That difference here is going to be the same as that difference here. This is my sigma star 2s. Okay? If we look at 2p, remember the first thing that's going to happen is you're going to, let me just give myself some space. I think I just, I apologize, but just trying to get the right space I can draw everything in without bumping into everything. Do 2p here. I'll do 2p here. Okay, so because of the weak interactions that we said existed, the first thing you're going to get is your sigma 2p, 2p. That's still higher energy. And then your pi, 2p, 2p. So both of these are 2p, 2p. Okay. Now when we draw our antibond, see this difference? It's going to be right here. See that difference? It's going to be right here. So this is pi star, 2p, 2p. This is my sigma star. Okay. So let me just draw the line so you know what goes where. So this energy difference here is the same as that energy difference there. Now I smeared my board. Okay. So, what's the difference? The difference when you look is that, remember when we were drawing, everything was central and it wasn't asymmetrical. Here, in a sense, it's asymmetrical. You can see that. What you can see is that my molecular orbital is closer to that atom in that electronic configuration if it's closer in energy. So in this case, my sigma 2s is closer in energy to my oxygen 2s. The sigma star 2s is closer to the nitrogen. So that's what happens when I have a difference in electronegativity and it's heterodiatomic. So if we went ahead and we filled up two, three, right? We filled up our electrons. 1, 2, 1, 2, 3, 4. Now let's go ahead and do exactly what we've been doing before. We're going to fill up all our molecular orbitals. So I have 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay. Now what that means is that the radical character of NO resides on the nitrogen more than the oxygen. So let's do a couple things. One, when we draw the Lewis structure, okay, of nitrogen, this more accurately depicts what we know from our molecular orbital diagram. The other thing is this. If you look at bond order, it's 1/2 of 1, 2, 3, 4, 5, 6, 7, 8 of 8 minus 1/2, 1, 2, 3. Okay, so what is my bond order? It's not 2, right? It's basically 2.5. So this bond that we've drawn as a double bond has its more characteristic of 2.5 bond, not 2. Okay, so it's a little shorter, okay, than a double bond, and it represents 2.5 bonds. So that's how we calculate bond order. Okay, so that's how we handle our heterodiatomic molecules. You've seen how we do strong interactions and weak interactions with boron and oxygen. And basically just practice, go from not worrying about electrons, just go make sure you know how to get your molecular orbitals first, and then put in your atoms to get your electron configuration. And that's how we approach it. I've finished 2 examples, one of boron and one of oxygen, and I've mentioned the terms paramagnetic. So let's do paramagnetic, and then let me do one more example for you. So paramagnetic, okay, we talk about it has magnetic properties. Because it has, okay, unpaired electrons. Okay, so what we find, it is attracted to a magnetic field. Okay, the opposite, in a sense, of paramagnetic is diamagnetic. Diamagnetic you used to think it had no magnetic properties, okay? But actually it's you barely measure it. That's why we originally thought it was no magnetic properties. It's weakly repelled in a magnetic field. Has very little previously thought, none. Magnetic properties. Now, on the electron configuration level, it's because it has all of their electrons are paired. Okay, so, and these properties apply not just to your diatomic molecules that we've been exploring, but also to the elements. So let's do a couple examples here. We had already done, we're going to do the weakly coupled atoms. We're going to compare oxygen and fluorine. Okay, so these are both weak sp interactions. Alright, so we'll do oxygen here, fluorine there, we have 2s, 2p, there's some space to draw these guys out. Fluorine here, it's purple, 2s, p, okay. Okay, and when we make our molecular orbital diagram, we have our sigma, sigma star, sigma 2p, 2p, pi 2p, 2p, and just give myself a little space, sigma, sigma star, sigma, and then lower this down just a little. So I can have a bit more space for my writing. Okay. Too light. And I'll start labeling everything in just a moment. Get these drawings down for you. Okay, so this is sigma 2s, 2s, sigma star 2s, 2s, sigma 2p, 2p, pi 2p, 2p, pi, again 2p, 2p, pi star 2p, 2p, another pi star 2p, 2p, and a sigma star 2p, 2p. We'll do a little this side. It's going to be, again, sigma 2s, 2s, sigma star, 2s, 2s, sigma 2p, 2p, pi, 2p, 2p, another pi, 2p, 2p, pi star, 2p, 2p, okay? And they look exactly the same because they're both part of the group that only has weak sp interactions, right? Versus when we compared boron and oxygen. One with strong sp interactions and one was weak. Okay, so let's take a look now at our electrons then. Just trying to indicate that's symmetrical. That's what this is all about. Okay. Alright, so now that you can see the symmetry of our molecular orbitals compared to our individual atoms here and here. So oxygen is 1s2, 2s2, 2p4. Okay. Whereas fluorine is 1s2, 2s2, 2p5. 1, 2, 3, 4, 5. So now we can start doing our electron configurations using our molecular orbitals. So 1, 2, 3, 4. I have 8. So 1, 2, 3, 4, 5, 6, 7, 8. So that's oxygen. We've seen this before, so it's good to know that I haven't made any errors, right? Here's that consistency. 1, 2, 3, 4, and I have 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. All right, so now that we have filled in our molecular orbitals and have done our electron configurations, what can we determine? Okay, so first of all, the magnetic properties, I have, this is a diradical, so I have 2 unpaired electrons. We know that it's paramagnetic because I have unpaired electrons. And the bond order we calculated earlier, 1/2 of 6 minus 2, so 1/2 of 4 is equal to 2. And that makes sense because when we draw oxygen again, we have the double bond. Okay? What can we say now about fluorine? Well, if you look at fluorine, it's not a diradical. Basically, it's diamagnetic. All my electrons are paired up. Okay? So that's nice. All my electrons are paired up, diamagnetic, and not only that, but the bond order is 1/2 of, this is 1, 2, 3, 4, 5, 6, 7, 8, minus 1/2 of 1, 2, 3, 4, 5, 6. That gives me a bond order of 1. And that makes sense because when we draw fluorine, don't we always draw fluorine with a single bond? Okay? So, the key though is not just looking at this, but looking The definition for paramagnetic is that I have an unpaired, at least one, an unpaired electron when I look at my electronic configuration. So oxygen is paramagnetic. If all of my electrons are paired, like in fluorine, it is diamagnetic. So it's weakly repelled as diamagnetic, and paramagnetic, it's attracted to a magnetic field. Okay, and that will be the end of Chapter 9.